Hello everyone. I'm Supratim Shaha, and I'm a PhD student at the Department of Physics at Indian Institute of Technology, Kanpur. So, I'll be giving a course on solid state physics, where I'll be talking about the basic properties of solids and how do they respond uh, when we apply an electric field or a magnetic field or this drives that we apply, and we are going to find the conductivity, the resistivity, and the various properties, the thermal conductivity. We are going to try and find out how do they respond to it. So let me first connect with the basic kinetic theory of gases, and it's important that I talk about this because at later point when we are going to talk about the electrical properties of the electrical conductivity of solids and metals in general, we will see that we are going to draw connections between this kinetic theory of gases and conductivity, resistivity of metals. So it's important that we study first and start off with the kinetic theory of gases. So let me just write down. Kinetic theory of gases. Let me just. So when we talk about kinetic theory of gases, we consider in a container a large number of gas molecules. Let's say let's draw it by and then move about randomly inside the container, right? The random motion inside the container, and these gas molecules, we consider it to be hard elastic sphere like particle. So they move out randomly inside the container and they undergo collisions within themselves and also with the walls of the container. All right. And the most important part to specify here is that they are non-interacting. Like they do not they do not attract between themselves or they do not repulse, so they are non-interacting. All right, but they undergo collisions between them, and the collision time, the moment or the instant they collide with each other, that is negligible compared to the time between two successive collisions. All right, so what we talked about is that the gas molecules, they move about randomly inside the container, and they are non-interacting. So let me just write down. So first point is that they are elastic sphere like particles. They undergo random motion. Doing so, they collide with the walls of the container and among themselves, right? And most importantly, they are non-interactive. Also, the collisions are perfectly inelastic, perfectly elastic, sorry, So there is no energy loss when there is a collision. All right. So, and as I said, non-interacting, there's no potential energy between them, only kinetic energy due to the motion of the particles. So what happens as a result of this random motion? So they collide with one molecule, and between two successive collision, the gas molecules, they traverse in a straight line and with uniform velocity, and they undergo another collision. And if we look at it grossly, like an average of it, uh, a molecule undergoing collision, these random collisions, as a result of this, the net average momentum of the molecules become zero. So this is as because the motion is completely randomized, so there is no definite direction as to where they are going to go between two successive collisions. So, but we can say that the kinetic energy between two successive collisions is equal to the thermal energy, where Kb is the Boltzmann's constant, and T is your temperature, right? And V is the velocity of the mean velocity of the gas molecules. All right. So between two successive collisions, the kinetic energy can be approximated by the thermal energy. All right. Now, these molecules, they have a net distribution, and distribution of what? Let Dn be the number of molecules having velocity between V and V plus dV, a small differential velocity dV. And if n be the total number of molecules inside the container, the fraction that gives the number of molecules having velocity between V and V plus dV is given by dn by n. Simply, this gives the fraction. Let us denote this fraction by the letter F. And I consider that you're probably familiar with statistical mechanics, thermodynamics. You all have learned in our basic courses that this dn by n, if we plot it, this F as a function of velocity, this follows a distribution like this, having a mean average velocity of V naught. This is the mean average velocity, and remind you that this is a temperature, let's say T1. And to state it, this is our familiar Maxwell-Boltzmann distribution that we have already familiar with. Right. Now, if one increases the temperature, we find that this distribution shifts. Simultaneously, sorry, simultaneously, this is like this. And the mean average velocity is given by V naught. Now, if we increase the temperature, this distribution spreads this velocity, and this is given by v1, and your this is T1 at temperature T1, and this is at temperature T2, and T2 is greater than T1. So this distribution shifts. This is our familiar Maxwell Boltzmann's distribution. So this is the distribution that the particles follow in response to a temperature or whatever they are subjected to, right? So they have a probability distribution kind of behavior. Now, to find the mean velocity of the gas molecules, what we are going to need is the very important equipartition theorem. To illustrate, let us consider in a 3D space a gas molecule which has, this is your X, and this is your C. This is your Vz, this is your Vy, and this is your Vx. This is your resultant velocity, right? So a gas molecule has velocity, has three components of velocity: Vx, Vy, and Vz, and has 3 degrees of freedom, as you can say, that is 3 directions like X, Y, and Z. So the equipartition theorem states that for each degree of freedom, the contribution of contribution to the contribution to the energy is given by half kVt. So energy here consists of only kinetic energy, because I have already said that the gas molecules are non-interacting. So the only contribution comes from the kinetic energy, but not the potential energy. As because the gas molecules has 3 degrees of freedom, the mean energy is given by 3 times half kVt. That is your 3 by 2 kVt. So for gas molecule, the mean energy is given by 3 by 2 kVt. And for velocity in each direction and for movement in each degree of freedom, the energy contribution to the energy comes out to be half kVt. Now, if this is the mean energy, the specific heat of the gas molecules is then given by Cv, that is dT, where T's temperature is 3 by 2 kV. Now, for n number of molecules, Cv turns out to be 3 by 2 in kV, which is equivalent to writing 3 by 2 R. So, see that the Cv is equals 3 by 2 R. This is constant, and moreover, it is independent of temperature. So at every temperature, it contributes 3 by 2 R. The mean energy is given by 3 by 2 R. So why am I drawing these conclusions, or why am I explaining so much about gases and all? To make the differences or the similarities between solids transitioning into solids from gases to solids easier. Like now, we can think about what happens to a solid then. What is the specific of a solid? What is the mean energy of a solid then? This question was pursued by Dulong and Petit in 1819, where they tried to measure the specific heat of a solid. So for gases, we already found out that it is 3 by 2R. And do we expect to see the same value for solids? So they measured the specific heat. What they found out, high temperature, they turned out to be constant, which was also the case for gases. Solids, interestingly, this is not 3 by 2R, but 3R. 3 by 2R. Furthermore, if they go down, if what they have seen as they went down to lower and lower temperatures, this distribution is nowhere constant. It goes down as CV proportional to T cubed. Even at sub-Kelvin temperatures, let's say at 1 or 2 Kelvin or 4.2 Kelvin liquid helium temperature, the contribution is CV is proportional to T. So that is a very grave difference that comes between solids and your gases. Dulong and Petit found out that at higher temperatures it is 3R, it is 3R. At as they go down to lower and lower temperatures, the dependence of T cube form, and at very low temperatures, sub-Kelvin temperatures or so, or maybe 1 or 2 Kelvin or so, the specific heat changes as T. As we go down more into the course, we will find out that this is due to phonon contribution, which are lattice vibrations, quantized lattice vibrations. And this contribution comes from the electronic specific heat. So the T cube dependence comes from the lattice, and the CV, or the specific heat at very low temperatures, but even sub-Kelvin of temperatures, comes from the electrons. So this is a very important difference that one found out between solids and gases. So now, as we are introduced to how solids behave differently, we want to learn about the electrical conductivity of metals. In general, about solids, so specifically about metals, right? So solids are comprised of, let's say, the ions, the ionic sites, and the electrons move about freely around it, all over the sample or the material that we are talking about. So these are delocalized electrons in a solid. The electrons move about freely inside the solid. Now we want to look at what happens when we apply an electric field, and how do the conductivity change in response to that electric field. So the first introduction that we are familiar with, or we are first introduced to a very popular experiment, which is the Ohm's law experiment. So it discussed about the electrical resistivity, or vice versa, the electrical conductivity of the of a material. So what happens for Ohm's law? So there's a sample we make contacts around it. So your power supply or whatever. So current flows in this direction, right? And we measure the voltage drop across the sample. Now, you are very well familiar with the voltage and current relationship. They are proportional and linear. Measure the voltage difference across the sample, found out that this voltage difference is linear with the current. And this proportionality constant is the resistance of the material, which is given by the slope of this straight line curve. So V equals I R. Now, if one wants to convert this in terms of electric field and current density, one can easily do that. So the voltage is expressed in this way. The electric field is given by V by L. That L is the length of the conductor. All right. Now, if a conductor has also a cross-sectional area, which is given by A, and L is the length of the conductor, then I is given by J into A. J is the current, is our current density. All right. Now, if we just plug it in, what we will get is E times L is I, which is given by J times A into R. All right. Now, E equals J into A divided by L into R. All right. Is equals R into L, A divided by L into J, which also implies J equals 1 by R A L into E. So this R A by L is your resistivity. All right. And the inverse of it, vice versa, the inverse of it, sigma, is your conductivity. All right. This we are all familiar with. So J time equals sigma E, E equals rho J. Sigma is your conductivity and rho is your alternatively your resistivity. All right. So different materials have different values of this resistivity. Or we talk about, let's say, for resistivity values, like metals, it is very, very low. Like, let me list out some very common values or properties of metals. Like for copper, it is 1.7 into 10 raised to minus 6 ohm centimeter, which is very, very low. For gold, it is slightly higher, that is 2.2 into 10 raised to minus 6 ohm centimeter. As you go down to bismuth, it increases by an order of magnitude. So for metals, the resistivity is very low, and for insulators, it is very high. For insulators, it can even go down to, go up to, say, up to around 10 raised to 6 ohm centimeter. You can imagine how high it is for insulators. So for a variety of materials, the resistivity values are different. All right. So we plot the rho, which is in centimeter with temperature as we increase it, as we change temperature. For insulators, the resistivity goes up as we decrease the temperature. But for metals, it goes down. And this is obviously you can understand. This is your 10 raised to 6, and this is 10 raised to minus 6. So the resolution or the how the graphs come about, they change. Like this cannot clearly see, but as you zoom in, you see that it decreases. Okay. So this is for insulators, and this is for metals. All right. There's a vast difference between these two variety of materials. For metals, the resistivity decreases with temperature. For insulators, it goes down with temperature, goes up with temperature. And semiconductors fall in between insulators and metals. So our first exposure to the resistivity or the conductivity of material was very well explained by the Ohm's law, and that we talked about. So for this lecture, let's just stop at this point. And in the coming lectures, we will be talking about the conductivity of metals, which was put forward by Trude's model. And we'll go on and see that it has some connections with the kinetic theory of gases. Or as we proceed in our coming lectures, you'll see that it has some sort of a connection. So I've dedicated this lecture to recapping some earlier knowledge that we had, which which may not be on top of our head, but recalling it helps. So let's just stop at this point and continue with our Rudess model in the next lecture.